Problem number 1. Suppose that a and b are real numbers such that at least one of them is non-zero. So we're expressing that condition via this expression. So the complex number a plus b times I is different from 0. And we're tasked with finding real numbers c and d such that this holds. In essence, we're being asked to find the complex number that is the multiplicative inverse of a plus b times I. So how do we solve this? Well, here's my original expression, and now I will multiply this term by this. So a minus b times I divided by a minus b times I, and this is just equal to 1. So since I'm multiplying with 1, nothing is being changed in the equality. So this is something I'm allowed to do. And now here we have a minus b times I, which will multiply a plus b times I in the denominator. And we have that if you have the difference of squares, so recall that this holds. So when we multiply, we get this expression over here. So we get a minus b times I divided by a squared minus b times I all squared. So when we square, we get a minus b times I divided by a squared. And since I squared is equal to minus 1, here we get plus b squared, which is equal to c plus d times I. And now, since we have a real number down here, we can split the fraction up. So we can write this in the following manner as a divided by a squared plus b squared plus minus b divided by a squared plus b squared times I. So we have that this is equal to this. So we have two complex numbers that are equal, and recall complex numbers are just ordered pairs, and ordered pairs are equal if their coordinates are equal. So c has to be equal to this, and d has to be equal to the imaginary part. So d is equal to this. And that's how we get c and d. So whenever you're given a and b, you can calculate what c and d have to be to get the multiplicative inverse of your given complex number. Problem number 2, we have to show that this complex number is a cube root of 1. Now this is not just the ordinary number 1, but this is the complex number 1. So 1 cube root of 1, of course, would be just 1. But it turns out with the complex numbers, we also have 2 more cube roots, and this is one of them. So let's show that this complex number is a cube root of 1. So how to show that? Well, we're going to split the fraction like this, and then we just cube, and after the calculations, we have to get 1. So just recall that if you're cubing a sum, this is how you do it. So it's just we plug in the numbers, we do some basic computations, and if you do the computations properly, you will get the following expression. And now this term and this term cancel, and we're left with 9/8 minus 1/8, which is just equal to 1. The only thing worth noting here is that when we have, in this term, we have I cubed, we have to determine what I cubed is equal to. Well, recall that I squared is equal to minus 1. So when we multiply both sides of the equality by I, we get that I cubed is equal to minus I, which we use over here to calculate this term. So we get the cube of this will be equal to this. There is minus I. So just rudimentary computations, nothing too fancy. Problem number 3. Problem number 3. Prove that this holds for all vectors in the vector space V. So what does this say? Well, it says that if I take some vector V and I take its additive inverse, and then I take the additive inverse of that additive inverse, I just get back the original vector. So let's show that this is true. We will calculate the following expression. So our term here, minus v, we just pull out minus v using the distributive law, and we get that minus v, which multiplies minus 1 plus 1, is equal to, well, minus v, this is just equal to 0, so we get minus v times 0, and when, well, any vector multiplied by the 0 scalar is just the 0 vector. So we have that this holds. Well, if this holds, then I can just add to both sides the vector v, and then we're just left with this expression, which is the statement we were trying to prove. So this holds for every vector v in the vector space. Problem number 4 says that prove that if a is some scalar and v is some vector from our vector space v, and a times v is equal to 0, then either a is equal to 0 or v is equal to 0, or they're both 0 at the same time. So let's show that from this. This follows. So we have that a times v is equal to 0. And now we go through two cases. So in the first case, let's suppose that a is equal to 0. Well, if a is equal to 0, then 0 times v is equal to 0. So we have that. In this case, a is equal to 0, and v can be any vector from the vector space, and this will hold. Well, since we have that this conjunction holds, we can relax it a bit and just get that a equal to 0 or v equal to 0 holds. Since we know that this is true, we know that a is equal to 0, so I can write this disjunction, and for the disjunction to be true, only one of its terms need to be true, and I know that a is equal to 0, so we have that this is true. So here's just a note about that propositional logic. So if you have some statements P and Q, if this is true, well, that means that both P and Q are true, so I can just take P, I know P is true, and then I can just say P or R, where R is completely arbitrary. Since I know that P is true, I'm guaranteed the truthness of the statement, so we've used that over here. So that was the case when a is equal to 0. Well, now let's suppose that a is different from 0. Well, if a is different from 0, then I can multiply both sides of this equality by the multiplicative inverse of a. So I'm just going to multiply by 1 through a, 1 divided by a, which we're guaranteed is different from 0, and we get that the vector v has to be equal to the 0 vector. So we have that in this case, this conjunction holds. We have that a is different from 0 and b is equal to 0. So again, I relax this to get the statement I'm after. Since I know that v is equal to 0 is true, I can just write the following disjunction. So a is equal to 0 or v is equal to 0, and this is true since v is equal to 0. So now when we unite both cases, well, in both cases we have that this holds. So this statement or this statement, which is just the same statement, so in both cases we have the statement that we desired to hold. So from this, it follows that a is equal to 0 or b is equal to 0. Problem number 5. We're given 4 subsets of the vector space f to the third, and we're asked to determine for each of these subsets whether it is a subspace or not. So let's go through them. Let's first recall that some subset of a vector space is a subspace if and only if I take two arbitrary vectors, elements from the set, an arbitrary scalar, and then we have to determine whether this expression, this sum, belongs to the set. If it does, then our set is in fact a subspace. So for A, we take two elements VW, we take some arbitrary scalar alpha, we form this sum, which equals to this, and now for a vector, an element to belong to our set, it has to satisfy the following condition. So the sum of coordinates like this has to be equal to 0. So now we have to determine whether this expression over here, this element over here, satisfies this condition, and if it does, then it will belong to our subset S of A. So we take this, these are its coordinates, and we form this. So we get this, we do some tidying up, and we get this, and now we use the fact that, well, V and W belong to the subset. So since they belong to the subset, they satisfy this condition, its coordinates. Their coordinates satisfy those conditions. So here we have that sum for V, and here we have that sum for W. So this is equal to 0, and this is equal to 0. So that means this sum over here is in fact, when you sum up its coordinates in that way, you do in fact get 0. That means that this belongs to S of A. So S of A is a subspace. For B, it's the same. So we just go, we form the sum, and we use the fact that the individual elements belong to S of B, so they satisfy the condition. So this is equal to 4, and this is equal to 4, and then we get that our V plus alpha times W is equal to this. Well, this is not always equal to 4 for this element to belong to S of B. This always has to be equal to 4, but for example, if I set alpha to be equal to 1, then I get 8. So this does not always belong to S of B, so S of B is definitely not a subspace. Now, for the subset C, well, the condition to belong to S of C is that when you multiply its coordinates, you get 0. So that means at least one of the coordinates has to be 0. So I take these two elements. So this belongs to S of C because, you know, there's 0, and this also belongs to S of C. But when I add them up together, I get this order triplet, and this product is not equal to 0. So this cannot be a subspace. And finally, for D, we get that the first coordinate has to be equal to 5 times the third coordinate for it to belong to S of D. So again, when we form the V plus alpha W, get its coordinates, and we try to find out what the first coordinate of that sum is equal to, well, we get it's equal to this. So we pull out the 5, and we get this. So the first coordinate is equal to 5 times the third coordinate. So our V plus alpha W does in fact belong to S of D. So this is a subspace. So that would be how to verify. Problem number 6. It asks of us to give an example of a subset of the plane, so R squared, such that the subset is closed under addition. So if I take two elements from the subset U and I add them up together, the sum stays in U, so closed under addition. The subset also needs to be closed under taking additive inverses. So if I take some element x, which belongs to U, then the additive inverse of x minus x also has to belong to U. And finally, U should not be a subspace. So we have to provide an example. of a subset that satisfies all these conditions. So let's figure out what subset to provide. So let's take some element x from U, and now since U has to be closed under taking additive inverses, we know that minus x also belongs to U. And now since U is closed under addition, we get that x plus minus x also has to be in U. That means that U needs to have 0 in it. So if I just were to form this set over here with 0 in it, well, this is a subspace. So we have to modify this a bit to get something that is not a subspace. Well, we can just add any ordered pair in here, and you add its additive inverse, and you will get the desired subset. So in this case, I just added the ordered pair 1, 1, and since it has to be closed under taking additive inverses, I also added the ordered pair minus 1, minus 1. And now you can verify that it's closed under addition. Whatever two elements you take, or three, and you sum them up, you'll always stay in U, and all the additive inverses are there. But this is not a subspace, since if I took the ordered pair 1, 1 and I multiply it by the scalar 2, well, the ordered pair 2, 2 does not belong to U, so this is not a subspace. So here's one example. Problem number 7. We're asked to give an example of a subset of the plane such that the subset is closed under scalar multiplication. So if I take some element from my set U and I multiply it with the scalar alpha, then the product has to be in U as well. And U must not be a subspace. So here is the example I came up with. So we will take this part of the plane and this part of the plane. So all of these points, including the axes. So how do we mathematically capture all of these points? Well, the points over here all are either positive, or we could just have 0, 0. So here are all the points with positive coordinates, and here are all the points with negative coordinates. So if I multiply the coordinates of any point over here, we get something that is greater or equal to than 0, and same goes over here due to them being both negative at the same time, so their product will be positive or 0. So we will define U to be the set of ordered pairs such that x times y is greater than or equal to 0. And now let's verify if our set U, defined this way, satisfies the conditions that we've been provided. So let's see if it's closed under scalar multiplication. So we formed the element alpha times U, where alpha is some arbitrary scalar. So this is how the coordinates of that element look. And now to test whether this element belongs to U, we multiply the coordinates, we get the following expression. Well, alpha squared is always greater than or equal to than 0, and x times y, due to how our set U is defined, is also greater than or equal to than 0. So this is greater than or equal to than 0. That means that alpha times U belongs to U. So it is closed under scalar multiplication. And now to show that it's not a subspace, well, here's a counterexample. So if I were to take, for example, this element over here, the ordered pair 0, 1, so this arrow, and if I were to take this arrow over here, which is minus 1, 0, and if I were to add them together, I would get this point over here, which is minus 1, 1. And well, this does not belong to my set U. So U could not be a subspace due to it not being closed under addition. Problem number 8. Let this F be a collection of subspaces, then the intersection of all of the subspaces contained within F is also a subspace. So we have to show that if you take a collection of subspaces and you take their intersection, be that a finite intersection, so for finitely many subspaces or even infinitely many, you will always end up with a subspace. So let's show that this is true. We take two elements from our intersection of all of the subspaces. We take some arbitrary scalar alpha from our F. And now, since x belongs to the intersection of all of those subspaces, that means that x belongs to the subspace S for all the subspaces contained within F. So also goes for y, just by definition of belonging to an intersection of sets. That means that x is contained within every subset, S in F and y as well. And now since y belongs to S for all S in F, and every S is a subspace, that means that S is closed under scalar multiplication, so we have that alpha times y also belongs to S for any S in F. And now we combine these two, so 1 and 2. Since S is a subspace, we have that this sum belongs to S for every subspace in F. So, since this belongs to every subspace in F, that means that it belongs to the intersection of all of the subspaces in F. So, we have taken two arbitrary elements, a scalar, and we've shown that this belongs to the intersection. So, that means that the intersection of all of those subspaces is also a subspace. Problem number 9. So we have x and y, two subspaces of our vector space V, and now we have to show that the following holds. So x union y is a subspace if and only if x is contained within y or y is contained within x. So let's start off by proving the implication from right to left. So let us suppose that either x is contained within y or y is contained within x. I will just go through the reasoning for one of these cases. It's the same for the separate case. So let's suppose that x is contained within y, like in this picture over here. Well then, x union y is just equal to the bigger set. So x is contained within y, so when I glue them together, take their union, I'm left with the bigger set, so y. And while y is a subspace, so we have that x union y is a subspace. Same goes for the other case. Now let's prove the other implication, so from left to right. So we suppose that the union of these two subspaces is a subspace. And now I take some x belonging to x and some y belonging to y. And now since x is a subspace, is contained within the union, so we have that this x also belongs to the union, and same goes for this y over here. And now, since this union is a subspace, we have that their sum also belongs to the union. And now we have that by the definition of an element belonging to union, this sum either belongs to x or it belongs to y. So I will just go through this case, and the same reasoning applies to the other case. So if x plus y belongs to x, well, that means that x plus y is equal to some, well, x with this dash, some element in x, some vector in x. Well, that means that I can just write y as this sum over here, and both of these elements belong to the subspace x, and since x is a subspace, this stays within x, So that means that y is equal to some element in x. So y also belongs to x. So from there we have that y is a subset of x. In the other case, we just get that x is a subspace of y. So we have shown what we wanted, that if the union is a subspace, then one of the sets is contained within the other. Problem number 10. So let us suppose that U is some subspace of our vector space V, and now we're asked to determine what U plus U is equal to. Well, we know for a fact that U is a subset of U plus U, since this sum is the smallest subspace such that it contains both subspaces which appear in the sum. In this case, just U. So we have that U is a subset of U plus U. And now we just take an arbitrary element from the sum U plus U. By definition, that means that V is equal to some sum of elements U1 and U2. And both of these elements belong to U, which is a subspace, so that means this sum also belongs in U. So we have that whatever element V I take from the sum, it also ends up being an element of U. That means that the sum is a subset of U. And now we combine 1 and 2, and by the definition of equality for two sets, we get that U is equal to U plus U. So if you have some subspace U and you add the subspace to itself, well then you're just left with U. You don't really change anything. It acts like a zero. Problem number 11. We have three subspaces of our vector space V, and we're asked whether 1. Is the operation of summing up subspaces commutative, and 2. Whether it is associative. So since when we sum up two subspaces, we just sum up the corresponding vectors from the subspaces, well, in our vector space V, addition of vectors is commutative, so U1 plus U2 is the same as U2 plus U1. So that gives us that 1 holds. So addition of subspaces, summing up subspaces, is commutative. And the same goes for associativity. So we just have, when we're evaluating this sum over here, we're looking at elements like this. And again, since we're in V, our vector space, that means that addition is associative. So this is just equal to this. And from that, it follows that this sum over here is the same as the sum over here. So summing up subspaces is commutative and it is associative. Problem number 12. So let U be a subspace of our vector space V. And now we're asked the two following questions. Under 1, does there exist a subspace W such that U plus W is equal to U? So we're asked, do there exist subspaces that act like the additive neutral element? And does there exist a subspace minus U such that U plus minus U is equal to the zero subspace? So do there exist subspaces that act like additive inverses? Well, for the neutral additive elements, we have that U plus the zero subspace is just U, and previously we've shown that U plus U is equal to U. So these are the neutral elements. Now for the inverse elements, if there existed a subspace minus U such that U plus minus U is equal to the zero subspace, we would have that U plus U dash, which belongs to minus U, would be equal to the zero vector. So we would have that U dash would have to be the inverse element of U. So if U belongs to our original subspace U, then we have that its inverse has to belong to minus U. And now, since minus U is a subspace, that means it's closed under scalar multiplication. So we would have that if minus U belongs to minus U, then we have that minus minus U, so this double additive inverse, which just equals to U, would also have to belong to minus U. So we would have that U has to be equal to minus U. And we also have that U plus minus U has to be equal to 0 subspace. So we have that once we replace minus U with U, we get that U plus U has to be the 0 subspace. Well, the only subspace that satisfies this is the 0 subspace. So only the 0 subspace has an additive inverse itself. Any other subspace, which is different from the 0 subspace, well, there just can't exist a subspace that would act like its additive inverse. Only the 0 subspace has an additive inverse. Problem number 13. So we have some subspaces U1, U2, and W. So these are subspaces of V, and this holds. So U1 plus W is equal to U2 plus W. And now we're asked, does it follow that U1 is equal to U2? So if this holds, does it follow that U1 is equal to U2? Well, it turns out that it doesn't hold, so we just provide a counterexample. So here we are in the plane, r squared, and I will let this be W, so just the x-axis, and I shall let U1 be equal to this subspace, just the regular old y-axis. And I will let U2 be any sort of tilted y-axis, so it's not like these two subspaces are not the same. But if you sum up the subspace W with U1, well, you just get r squared. You get every point in the plane, and the same in this case. So W plus U2, you can reach every point in the plane, so their sum is r squared. So we have that this holds, but obviously U1 is not equal to U2. So also, since we have this picture in front of us, if we were to strengthen, for example, this equality and say that U1 direct sum of W is equal to U2 direct sum with W, it also doesn't follow that these two subspaces have to be equal, since again, this is also a direct sum. W and U1 form a direct sum of the plane, and W and U2 also form a direct sum of the plane. And again, these two subspaces are not the same.